Welcome to the Deep Dive, where we unpack your source material and find the insights that matter most. Today we're diving deep into the life and the monumental legacy of a figure who not only defined modern computing, but then in this amazing twist of intellectual honesty, spent his later years trying to undo the very constraints he himself helped create. We are talking about John Backus.
That's exactly right. Our sources paint this really compelling picture of a man whose career had, three profound and very distinct acts.
Three acts. Okay.
Act one, inventing the first widely used high-level language, Fortran. And this just instantly brought computing out of these specialized labs and into the hands of scientists and engineers.
Right, for the masses.
So the scientific masses, yeah. Then Act two, formalizing how we even describe a language's structure through the notation we now know as Backus-Naur form, or BNF, that really cemented the intellectual foundations of the field.
Okay.
And then Act three, delivering this fundamental philosophical critique of the entire programming paradigm he helped establish, that sequential, procedural von Neumann style.
So our mission today is to understand not just these three influential contributions, but how they all connect. I mean, how the necessities of the 1950s led to a revolution.
Which then demanded a formal structure.
And then that structure, I guess, revealed its own limitations,
Right?
which led to a philosophical overhaul.
Exactly.
And Backus wasn't just foundational, he was heavily decorated. We're talking about a recipient of the National Medal of Science in 1975 and the ultimate prize in computing, the ACM Turing Award, in 1977.
And that Turing Award specifically recognized his, quote, profound and lasting contributions to the design of practical high-level programming systems, which is Fortran,
Right.
and then for the formal procedures he created for specifying programming languages. That's the BNF part. It's this extraordinary recognition of both a practical system builder and, a deep theoretical formalist.
A builder and a thinker.
Yes. But what's truly fascinating, and what our sources really highlight, is that before all the accolades, before the global scientific impact, his path was, well, it was anything but straight.
Yeah, this isn't the story of some childhood prodigy.
Not at all. It's the story of delayed genius, if anything.
Okay, let's unpack this and start right at the beginning. The surprisingly circuitous route John Backus took to even find his way into computer science.
If you track his early academic record, it's honestly just striking how much he struggled to find any kind of focus. He was born in 1924, grew up in Wilmington, Delaware, and he started at the Hill School in Pennsylvania, where he did not exactly thrive.
Right. He later said he was just terrible at keeping track of things.
Which is pretty ironic for the guy who would later invent the formal notation for language grammar, right?
Struggled is definitely putting it politely. I mean, the sequence of events right after high school, it looks less like a path to greatness and more like a young man just running away from any kind of structure.
Oh, completely. He enters the University of Virginia to study chemistry, and that lasts less than a year.
Why? What happened?
The records show he was expelled for poor attendance. So we're talking about a mind that would later design these systems for ultimate efficiency, and at first he couldn't grasp the simple efficiency of, showing up to class.
And this was the mid-1940s, so World War II is in full swing. That expulsion leads directly to conscription.
It does. And for a lot of intellectually restless young men at the time, that proved to be a surprising and I think necessary reset button. But it wasn't an immediate jump into high tech.
No.
He starts as a corporal in the U.S. Army, commanding an anti-aircraft battery down at Fort Stewart, Georgia. It's a very gritty, mechanical, command and control kind of role.
But it's during his time in the service that his actual aptitude starts to surface, right?
Absolutely. He scores remarkably high on one of those military aptitude tests, the ones designed to sort personnel. And that score convinces the Army to completely shift his path. They saw this raw, high-level processing capability and sent him to study engineering at the University of Pittsburgh.
So the military basically recognized this latent talent and gave him the structure he couldn't impose on himself. But even after that, he's still not in computer science. The search continues.
It does. From Pittsburgh, he moves again. He transfers into a pre-medical program at Haverford College. He's still searching for that field that would engage his unique blend of practical problem solving and abstract thought. And this is where his biography takes a really unusual turn.
The health crisis.
A major personal health crisis.
And the way he responded to it, I mean, it's such a strong indicator of the engineer he was about to become.
It really is. During a hospital internship, he's diagnosed with a cranial bone tumor. It was serious, life-threatening. But it was successfully removed, and the procedure resulted in a metal plate being installed in his head.
Okay.
After recovering, he tries medical school at Flower and Fifth Avenue Medical School, but, much like his attempt at chemistry, he just found it uninteresting. He dropped out after only 9 months.
So his mind just couldn't tolerate the rote memorization, it sounds like.
I think so, especially after the intellectual challenges of war and recovery. So yeah, he's failed out of one college, dropped out of 2 subsequent programs, and he's had major brain surgery. That's a really disruptive period.
And then comes the second operation. This is the anecdote that I think just perfectly demonstrates his mindset.
It is perfect. He needed the original plate replaced. But instead of just accepting the standard surgical solution, what does he do?
He designs the replacement himself.
He designed it himself. He ultimately had a metal plate of his own design installed in his head.
It's the perfect metaphor. He was innately a system designer, solving a problem of necessity with custom engineering, even when the system was his own body.
Exactly. He received an honorable medical discharge from the Army in 1946, and after that, he moves to New York City and initially trains as a radio technician.
And that's the spark, that hands-on technical work.
That seems to be it. It illuminated the underlying principles, the mathematics of systems, and that's what finally captivated him. He fell in love with pure math, and through that, he found his field.
So he enrolls at Columbia.
He enrolls at Columbia University, earns his bachelor's in 1949 and his master's in 1950, both in mathematics. He joined IBM that same year, 1950. And that's when his life as a revolutionary truly begins.
And once he was at IBM, the raw, demanding nature of early computing just forced him to address the biggest practical problem facing the entire industry: usability.
It did. And that brings us to Section 2, all about Fortran. And to really appreciate its impact, you have to ask, what was programming even like when Backus joined IBM in 1950?
I think in the modern age, we just take compilers and high-level languages for granted. But the difference between what we do and what Backus was doing, it's almost impossible to really grasp.
It was unbelievably difficult. His early work involved the Selective Sequence Electronic Calculator, the SSEC. It was a marvel of electromechanical computing, and his first major project was this practical, high-stakes, but just painstakingly difficult task.
Calculating the moon's position.
Calculating the positions of the moon, which, required continuous, accurate data.
So the reality of doing that was just manual, tedious labor. You were writing code directly in machine language or, assembly at best. You weren't writing A if E plus C.
No, not at all. You were writing instructions for register management, for memory fetches, for carry operations. You had to have this intimate, deep knowledge of the hardware architecture.
Down to the specific memory cell.
Right. Down to which memory cell held which variable and how to sequence every single tiny operation through the accumulator. The programmer's job was fundamentally mechanical. It was just translating mathematical logic into this excruciating sequence of hardware-specific instructions.
It was slow, error-prone.
Incredibly error-prone. And it required immense amounts of time just to translate the math into something the machine could understand. The computer's efficiency was completely bottlenecked by the programmer's ability to communicate with it manually.
So the computer could calculate in microseconds, but it would take a programmer weeks to just manually lay out the instructions for a single complex problem.
That's it, exactly. The translation time just defeated the speed of the machine. And this inherent difficulty was the bottleneck. It was preventing computers from becoming truly useful scientific tools.
And Backus saw this.
He saw it clearly. And his first step towards solving it was a language called Speedcoding.
The stepping stone to Fortran.
In 1953, he developed Speedcoding for the IBM 701 computer. Our sources note this was the first high-level language created for an IBM machine. It wasn't Fortran yet, but it was this critical proof of concept.
What did it do?
It introduced basic forms of abstraction. It essentially let programmers write code that was interpreted by a layer of software into the necessary machine instructions. It just immediately showed there was a huge need for this.
It proved abstraction was possible. And by 1954, the difficulty of low-level programming was becoming a real crisis for IBM, commercially and intellectually. This is the inflection point.
This is it. This is where Backus assembles the team to define and develop Fortran.
Formula translation.
Formula translation, designed specifically for the new IBM 704 computer, which was significantly more powerful than the 701. And Backus's mandate was revolutionary. He had to create a language that was easy to write, that looked like algebraic notation.
And this is the key part. That could produce code nearly as efficient as handwritten assembly.
That was the fundamental challenge. If the compiled code was too slow, scientists would just ignore it and go back to the old hard way.
So Fortran wasn't just about making programming easier, it was about creating an efficient compiler that could manage all the hardware logistics better than a human could do it manually.
That is the structural significance. Fortran became the first widely used high-level programming language because it solved that efficiency problem. Think about something like array indexing.
Okay.
In assembly, if you wanted to access aij, you had to manually calculate the memory offset based on the array's starting address, the column size, and the indices I and j. It was tedious.
And Fortran handled all that for you.
All of it, automatically, and the compiler did it optimally. That's the real revolution. It revolutionized computer accessibility by abstracting the machinery away. Programmers could write formulas that looked like x, y plus z, I plus 2.0, and let the compiler worry about the registers, the memory allocation, all of it.
So suddenly computers were practical for the people who actually had the problems to solve. Physicists, chemists.
Structural engineers. This single innovation unlocked computing for scientific and engineering research globally. It shifted the entire bottleneck from how do I talk to the hardware to what mathematical process do I need to automate.
And that paradigm shift was recognized pretty quickly. The success of Fortran led to Backus getting the WWII Award in 1967.
Yes, it did. But as soon as high-level languages were successful, they created a new, deeper, more philosophical problem. Definition, exactly. Once you have a powerful tool like Fortran and then dozens of other languages following its lead, you need a way to make sure everyone agrees on what the rules of that language actually are.
Which leads us directly into Act 2 of his career. This is Section 3, defining the language of languages, the Backus-Naur form, or BNF. So once these languages emerged, the technical community needed a precise, universal dictionary for the grammar. Before this, descriptions were just written in English, which is, inherently ambiguous.
Disastrously ambiguous, and the catalyst for standardization came from an international context, mostly around the development of the Algiol family of languages.
And Backus was a central figure in that.
A central figure. He served on the international committees that developed both Algiol 58 and then the highly influential Algiol 60.
And it's important to stress, Algiol 60 didn't achieve the commercial dominance of Fortran.
Not even close.
But it became the de facto standard for publishing algorithms, just because of its clean, structured design.
And that design elegance was a direct result of the clarity of its formal definition, which was entirely due to Backus's invention. In the context of the UNESCO report on Algiol 58, Backus invented the notation we now know as BNF.
So what exactly is BNF? For someone who hasn't, done a deep dive into compiler theory, it sounds esoteric, but it's foundational.
It is. BNF is a formal notation that can describe the syntax of pretty much any context-free programming language. To understand how revolutionary it was, think about what came before. If I used English to define a loop, I might write, a loop starts with DO, then a variable, an equal sign, an initial value, the word TO, a final value, and so on.
Right, which sounds clear enough, but then you get into all the edge cases. What if the variable has to be an integer? What if the initial value can be a complex expression? English just gets messy with footnotes and exceptions.
It gets messy immediately. BNF provides a set of concise production rules that just eliminate all ambiguity. For instance, a simplified BNF rule might look like this: expression. Term expression plus term.
Okay, break that down.
It's defining an expression recursively. It says an expression is either a single term or it's another valid expression followed by a plus sign and another term. It's a mathematical definition of grammar.
So it takes all the ambiguity of natural language and just replaces it with mathematical certainty.
And that precision is why BNF matters so much for compiler development. The ability to formally specify the language allowed for the eventual automation of building the compiler itself.
The translator.
Yes. And that's why BNF was explicitly cited in his Turing Award. It established the theoretical bedrock for the field. Instead of a compiler writer having to interpret some ambiguous English manual,
they could just read the mathematical grammar in BNF and program their compiler to recognize tokens according to those exact rules.
It was transformative. It introduced rigor. Now, there were some other approaches. Our sources mentioned Lisp and APL had their own notations, but by the 1970s, the Backus-Naur context-free specification had become the industry standard.
And that standardization was critical because it enabled automated tools.
Things like Yak, yet another compiler. Tools like Yak let developers feed a BNF description of a language to a program, and that program would automatically generate a huge chunk of the necessary parsing code for a compiler. This just massively accelerated the creation of new languages.
So this lets us connect the dots perfectly. Fortran solved the problem of writing programs efficiently.
Making computing practical.
Right. And then BNF solved the problem of defining programs rigorously, which made language design systematic. It really formalized computer science as a discipline.
He had basically given the world its first great high-level language, and then the mechanism to define every language that would come after it.
And if he had retired right then, in 1970, he'd be remembered as one of the greats.
One of the all-time greats. But he wasn't finished. In the late 1970s, he enters Act 3, a phase that involves a deep, self-imposed critique of everything he had helped build.
And this is where his career becomes truly fascinating. In the late 70s, after achieving all this fame for creating the dominant programming paradigm, this sequential procedural style, he pivots to critique it fundamentally.
It shows a mind that just wasn't interested in resting on past achievements. He was constantly striving for a more elegant, more expressive form of computation. And the public declaration of this pivot was his 1977 Turing Award lecture.
The lecture that shook the industry. Can programming be liberated from the von Neumann style?
That title is the whole thesis. He was railing not against Fortran specifically, but against the foundational hardware architecture that Fortran was forced to obey, the von Neumann architecture.
Okay, we need to define the von Neumann style clearly because it basically defines almost every computing device we use today.
It does. The von Neumann architecture dictates that the computer operates through a single channel connecting the CPU where the processing happens, and memory, where data and instructions are stored.
And the CPU just executes instructions one after another, sequentially.
Sequentially, constantly fetching data from memory, processing it, storing the results back, one word at a time. Backus called this the von Neumann bottleneck.
Because the CPU spends most of its time just waiting for data to be shuffled back and forth across this narrow channel.
Yes. And Backus argued that our programming languages evolved to just mirror this mechanical process. Procedural languages like Fortran, C, Pascal, they were all designed around the fundamental concept of the assignment statement.
The assignment statement being, X plus 1 exact.
Exactly. And that statement is nothing more than saying, go to this specific memory location, X, fetch the value, do an operation like +1, and then store the new result back in that same location.
So he's saying that by making Fortran successful, they had basically institutionalized a constraint that was imposed by the hardware.
That's the core of his critique. He argued that this style was fundamentally limited because it forces the programmer to focus on the mechanical, low-level details of data movement, what he called word-at-a-time programming, rather than the high-level mathematical structure of the problem itself.
So he believed programmers were being forced to think like the machine's memory fetcher, not like a pure mathematician.
Yes, a loss of expressive power and elegance. He saw the entire industry as being trapped in an imperative morass, where programs were just a sequence of state changes rather than clean mathematical transformations.
And this lecture is sometimes seen as his apology for creating Fortran. Is that accurate?
It was misinterpreted. It wasn't an apology, it was an intellectual evolution. The problem was that his proposed solution, function-level programming, or FLP, was often mistakenly confused with existing functional languages like Lisp.
Which used lambda calculus.
Right. And Backus was aiming for something different, something algebraically cleaner. His antidote was to move toward a style that focused entirely on combining functions to transform data rather than assigning values to variables.
And to explore this idea, he designed a language called FP.
FP for function-level programming. It was his direct attempt to embody these ideas, and it was heavily influenced by Kenneth Iverson's APL.
A programming language,
Yeah.
which was already pretty radical.
Very radical. It was focused on array processing and used this non-standard character set to denote these powerful, primitive operations that worked on entire arrays at once. FP inherited that spirit.
So how did it work? No variables, no loops?
No. It operated using a small set of combinators, which are functions that take other functions as arguments and combine them to create more complete functions. The key is the programmer never directly interacts with variables or assignment statements.
So if you wanted to sum a list of numbers.
You wouldn't write a loop and assign the running total to a variable. You compose a function that maps an addition operator across the entire data structure at once. It was an algebra of programs.
That sounds incredibly rigorous, but also a huge departure from the mainstream. How was its adoption?
Adoption was niche. An FP interpreter was distributed with the 4.2 BSD Unix operating system, which is interesting, but implementations were few. It was used mostly for educational purposes.
The conceptual leap was just too big.
Too big for an industry already so heavily invested in procedural C and Fortran. But Backus didn't give up. He spent the latter part of his career trying to refine this concept, creating a successor language called FL.
FL, for function level.
Right.
What was the fate of this second attempt?
FL was a long-term, intensive internal research project at IBM. Backus was focused on making it even more rigorous so that you could mathematically manipulate programs the way a mathematician manipulates equations.
But unlike Fortran, which IBM pushed globally, FFL just stayed internal.
Unfortunately, yes. Development stopped when the research project finished, and the source code for the compiler was never made public. Only a few documenting papers are left.
Why do you think it failed to gain traction when the original was such a colossal success?
It was a collision of philosophy and timing. By the 1980s, when FL was being developed, functional programming was gaining traction, but it was centered around lambda calculus and static typing languages like ML or what would become Haskell.
And FL was different.
FL, following that APL lineage, was philosophically distinct. It focused on the concatenation of primitive operations, using these powerful array-centric operators. It felt alien to the academic functional movement.
So his vision was kind of caught between two worlds.
Exactly. It was caught between the highly practical, procedural world he was critiquing and the mathematically rigorous lambda calculus world, which he didn't fully embrace either.
But the ideas didn't die.
Not at all. The legacy of FL is seen clearly in later versions of the J programming language, which is Iberson's successor to APL. J is a modern, powerful array processing language that carries many of the structural insights and the mathematical elegance that Backus was searching for in FP and FL.
So his critique, if not his specific language, was enduringly relevant.
It was. His core philosophical drive continued to influence that entire lineage of array processing languages.
It is just so rare to find a figure in any field who so fundamentally shaped its practical foundation, then formalized its theoretical structure, and then stood back to deliver a devastating philosophical critique of the entire system.
It really is. He created the digital freeway, established the rules for building all the future roads, and then said, you know what, this whole infrastructure is fundamentally limiting our speed. It speaks to his relentless intellectual energy. He was never satisfied with good enough.
So his career spanned the absolute necessity of early computing, from the manual toil of calculating lunar positions on the SSEC to the abstraction of speed coding.
The revolution of practical science with Fortran.
The formal definition of all language structure through BNF.
And finally, the profound philosophical critique of that whole world with FP and FL.
And the recognition he received truly reflects that triple legacy.
It does. IBM Fellow in '63, the McDowell Award in '67, the National Medal of Science in '75, followed by the Turing Award in '77. Later honors included the Draper Prize in '93, and he was named a Computer History Museum Fellow in 1997.
He passed away in 2007 in Ashland, Oregon, leaving behind this monumental, complex, and ultimately challenging legacy. And as a final, slightly more whimsical honor, the asteroid 6830 John Backus was named for him.
A true giant. But for the learner, for you listening to this, I think the most important part of Backus's work is the lasting question he posed.
The idea that programming is constrained not by our intelligence, but by the physical architecture of the computer.
Right. If Backus, the creator of Fortran, ultimately argued that the underlying sequential von Neumann style architecture limits how powerful and expressive our programs can be, this raises a really persistent and important question.
And that is?
Nearly 50 years after his critique, are the programming languages you use, Python, Java, JavaScript, are they still fundamentally constrained by that sequential, word-at-a-time, memory-shuffling design of the processors they run on? Or have model paradigms like object-oriented design or massively parallel processing truly found ways to liberate us from that mechanical sequence? It's something to consider the next time you design a system or write a line of code. Are you instructing the machine on the logical steps of your problem, or are you just efficiently managing the flow of data across the von Neumann bottleneck?